Hello, everybody, and welcome to this RISE Learning Machines seminar. And hope you all had a nice summer. It's been a while. We're eager to get started with these seminars. RISE is Sweden's research institute, the public one. We're state-owned. We have nearly 3,000 people working on a wide array of things. The computer science department works on applied AI projects for the benefit of society, and we organize these seminars every week, with just very few exceptions. This meeting will be recorded, and if anyone wants to be removed from this recording, please let us know and just drop me an email afterwards. Make sure to check out our collection of great talks on our YouTube channel. Today, it's my absolute pleasure to introduce Zahra Taghiyar Renan, who is a PhD candidate at Halmstad University and who is about to defend her thesis in March next year. So the topic today is from domain adaptation to federated learning. And with that said, I will hand over the word to you, Zahra.
Great. Thank you for introduction. Let me share my screen. I assume you see my screen, yes?
Yes.
Okay. Okay. Great, thank you. Thank you for introduction. And hello, everyone. Actually, here I want to talk about domain adaptation and federated learning. And it is a topic that I work mainly for my PhD on that. And I really appreciate this opportunity you provided that I can share some part of my work on this topic. So here I will start by domain adaptation, and then we will move to federated learning. We will connect it to the federated learning. But before going into details of these topics, let me at first mention the application, and it is predictive maintenance. I mainly focus on the predictive maintenance problems. And I'm mentioning this one because during the seminar, I will bring some example from this area. And it is mainly for fault detection or a state of health prediction of different equipments or remaining useful lifetime. So I have some example from domain adaptation, and also we want to analyze the situations in the federated learning, and I use example from this area, and mainly for the state of health prediction. So this was the reason that I wanted to mention this one. And now I want to start here. And we all know that when we want to start working with AI machine learning, the first thing is data, and the data collection and actually getting data together. We know that it's a challenge everywhere, and it is because of different things. And one of the things is that we have diverse systems and there are diverse data sources. So we know that there are many challenges with the data, maybe from labeled or unlabeled or something like this, but even collecting data is another one. So we know there are different data owners, and the question is that if data owners will share their data with us or not. Sometimes they'll share, and okay, it's great, but does it solve our problem? And we can say no, because again, because of the diversity that we have in the different situations with different data owners, there is heterogeneity between the data. And even also we have access to data, is still that heterogeneity, and even when they have the same features, the heterogeneity is problematic. And sometimes the data owners don't share their data. So here, not only we don't have data, and the data also has heterogeneity. Okay, and it is when we go to federated learning, and it is exactly where domain adaptation and federated learning, and specifically heterogeneous federated learning, because we want to talk about data heterogeneity. So it is here that domain adaptation and heterogeneous federated learning meet each other. So we first start from domain adaptation, that we assume that we access data, even they are from different data owners. So as I said, at first I start by domain adaptation, and as an example for domain adaptation to see how it is effective for solving real world problem, I will have domain adaptation for regression method, and after that I will go to federated learning, and in this part I will analyze the effect of data heterogeneity in federated learning, and for this this part we will see the results for both experimentally and theoretically. So about domain adaptation, but before going into details, why we are talking about data heterogeneity and why it is important for us, and it backs to the main assumption of machine learning, that we know that it says that training and test data should come from the same distribution. Because when we validate our model, we assume that this data that we are validating our model is from exactly the same distribution. And we calculate the generalizability of our model based on this assumption. But in real world, it doesn't hold true always. One example is that we want to predict the state of health of battery on buses. And buses are in two different countries, for example, Sweden and Spain. And assume that even we have access to data, but when we train a model on data from Sweden, that model may not perform well when we use for Spain. And its reason is differences that there exist between Spain and Sweden, temperature, geography, and lots of it. And we call it as dataset shift. The first figure is what is assumed, that we have training and we have test data exactly from the same distribution. But in reality, sometimes this training and test are separated from each other, or there's a difference between them. Now let's rephrase the terms. Instead of training and test data here, let's call them source data and target data. And now this is the domain adaptation job. That domain adaptation should unify the distribution of the source and target data, so that after that we will have train and tests from the same distribution. For domain adaptation, there are many different ways to do that. But mainly, if we want to summarize them, they work in like this. We have source data and target data in original space, the feature that we get. And the domain adaptation method, they train a feature extractor, and by that feature extractor, we have source and target in a constructed space. And now in the constructed space, source and target are supposed to have the same distribution. So what domain adaptation do is removing the discrepancy between source and target by training that feature extractor. Now that we have data, source, and target, which are unified in the constructed space, we can have a predictor on top of that. It can be classifier, regressor, or anything. So this is the whole story of the domain adaptation generally. But why we are talking about it? We need to remove that discrepancy. I want to talk a bit theory behind that. I will have 2 or 3 this type of slides, but we want to see what happens in the theory, that we need to remove that heterogeneity. There are some assumptions that we consider X as input space. We have distribution, and we consider a binary classification problem here, F. And we have a hypothesis, and the risk of hypothesis that is the difference between the data labeling function and what we learn. So by this assumption, we know that in learning theory, this is the first thing that we learn when we start learning machine learning, that the error or the risk of the hypothesis is upper bounded by the empirical risk plus this term. That empirical risk is the error that we get during training. And this term is, it says that it depends on the number of the data that we have. When we have lots of data, this term would be 0. And this term will be 0, and then it will be upper bounded only by the risk in the training. So it is for traditional machine learning, but in domain adaptation, these are the things that we say. We have source and target, then we have distributions, and then that equation that we had will extend to this one. Again, we have these two cases. Maybe if I go here, it is better to compare. It is this part. It has a bit delay. Yeah, this part, the first and second term are similar to what we had, but the difference is here, D of H delta H between distribution of source and distribution of target. What does it mean? It means that if, of course, we have source target and we can train a model on source and use for target. It's okay, but if we want to improve the performance of that model for targets, we need to minimize this term. And it means we need to remove the discrepancy between source and target to improve the precision or the accuracy of our model.
Are you coming to how you define the D here?
No, actually.
Okay.
Yeah. Because it would be different if I wanted to talk about the details of that, but I want to go into federated learning. But anyway, just shortly, I can say that the D is distance between two distributions, and it is defined over H delta H space. What is this space? It says it is defined here that it's defined by the XOR of two different hypotheses. So it says it's true if one of those true. And it means the conflict between two hypotheses. If they are in conflict, we say that they are different from each other. Yeah. Or if we want to say simply a sample where in some, for example, for a company is totally normal, can be faulty, can be considered as a faulty data in another company. And it means that they are in conflict with each other.
These two different hypotheses, are they sort of trained on the two different domains? Or why do we consider those hypotheses?
Yeah, exactly. Because here we have DS and DT. DS is data of the source, and DT is the distribution of data of source, and DT is distribution of the target.
Yeah.
And this hat means the distribution of the data in the constructed space here that I had.
Okay.
Yeah, here in constructed space. So it means that in this constructed space, we should minimize this the discrepancy between these two data. Okay, I had this part, this generalization bound for the domain adaptation, because I after that I want to extend it to the federated learning. So until here we talked about the data distribution for domain adaptation, but there is one more thing that is important for domain adaptation, and it is about task. Is it really different when we want to talk, when we want to solve a classification task or a regression task for domain adaptation? So for this one, we need to go into details of the domain adaptation. a bit detail of that. We start with domain shift and dataset shift and domain adaptation. We said that distribution are different from each other. So probability of X and Y are different from each other, from source and target, but it can be happen in two different ways. Sometimes only the difference is on X, marginal distribution, without considering Y. It means probability of X is different of probability of X of target here. So in this case, we don't talk about Y. And here, we just need to minimize the distribution distance between marginal distribution of source and target. And there are lots of methods like that use, for example, adversarial methods like DANN, which is the, I assume, is the most well-known domain adaptation, or some other methods, KL divergence or MMD, they use to minimize the distance. And we call this as covariate shift. But the difference can be in Y, in conditional distribution. So here, what usually people do is that they use exactly the same methods here for that, but they do that per class. For example, they minimize the distribution of the data from class 1 of source and class 1 of target. So they do per class. And in this way, they remove that heterogeneity. We call that one concept shift. For the first one, that is covariate shift, we didn't talk about Y. So we only consider X. So in this case, every method that we have, we can apply for both classification and regression. There are many number of the papers that work on this, and we can simply change the predictor to regression or classification. But for concept shift, it's a bit different because the main method is that they minimize the distribution per class, and it is if it is proposed for classification, it makes sense because we have a limited number of the classes, but what about for regression? And it makes different. So if we want to solve the concept shift for regression, we need another method other than classification. Here, just to see one example to see how it makes sense in the reality, I have one example here that we apply domain adaptation to real world problem, and it is exactly domain adaptation for regression, and we use that for the state of health prediction of the batteries of vehicle. So it is like that. It is about buses, and we consider different types of buses as different domain. It's because they are different from each other. So we have single decker buses, we have double decker buses. Okay, and how we solve that, how we actually remove that discrepancy between them, we propose a loss function like this. Xi is from single decker, Xj is from double decker. In the original space, we define a kind of similarity between any two samples. And then we wanted to, we need a feature extractor, and now the samples are in the new constructed space. Yeah, and again here we define a similarity. In the original space, we define similarity based on their Y. So, and in the constructed space, we define their similarity between their distance. So if two samples, the state of health of two samples are somehow similar to each other, these two samples should be close to each other in the constructed space. And in this way, we force the samples, is almost the same as OH, to be near to each other. And for this one, we propose this loss function, and we trained, we use this Xiaomi's type network to train this feature extractor. It gets a pair of samples and it constructs the feature extractor, and here we have the samples in the constructed space. And then we use feature extractor. It is exactly what I showed in the first slice of domain adaptation. And then on top of this one, we train a linear regressor. So for the results, I want to compare how it affects, how this domain adaptation affects the result when we use that versus when we don't use. Here we use double-decker, the samples from double-decker buses for training and test, and this is the results of the results are in terms of mean absolute error. So this is like after that we merge sample from single decker to double decker. We just merge them without doing any domain adaptation. We have some sample from here, some sample from here, and we use for training and then test on double decker. And we see that the results is worse than the previous one. And now, after that, we apply domain adaptation. We construct new space, we unified single and double decker, and then we use the same regressor. And we see that in this way, domain adaptation helps us to improve the precision, the performance of the.
In the two top lines, you have both single and double in the training set.
In the yes, for the first one, just double. In the second one, single and double without domain adaptation.
Yeah.
And for the third one, single and double decker we have, and we apply domain adaptation on it.
So you have both domains in the training set.
Yes. Mm. Yeah, it is for domain adaptation, we need to have access. Mm. We always have access to data from all of the domain. We apply domain adaptation in that, and then the only job of domain adaptation is unifying the distribution of them. Mm. So in this way, we can see that how merging heterogeneous data to each other makes the situation worse than what we have, and here by domain adaptation, we can improve the results. Again, with the same method, but we define another problem. We assume that we have samples from two different countries, C1 and C4. And here, there's a difference. We assume that we have lots of data from C1, country C1, but not that much from C4. And again, and if I want to be more precise, we use lots of data from C1 and data from only one bus in C4. And then we apply domain adaptation. And then this is the result on C1, and this is C4. Our method is the last one, dark. And we see that how it is different from, for example, when we use only linear, or even when we use only source data. And one more example here, instead of only two domains, we consider 5 different domains. Again, it is for the prediction of the state of health of the buses. And here, we assume that, okay, we don't have that much data from different domains. We have 5 countries, and we assume that, okay, we have data from only one bus in each country. Then we gather this data, we apply domain adaptation, and then here we evaluate per country.
In the previous slide, you had DANN as a baseline. Didn't you say DANN was only for classification?
Okay, here we changed the exactly. I had.
So it's not regression now.
No, we changed it to the regression, and exactly here I had DANN here.
Yeah.
And I told you that it is when we have a method here in this category, we can simply change the predictor and use that for the. For example, it is designed for classification, but because in the domain adaptation part, it just focuses on X, we can simply change it to the regressor. Okay. And exactly here, we did the same. We defined DANN we changed the predictor to regressor, and we use. Yeah, it was the results of this paper. If you like to see more details of that, this is the paper that you can check. Anyway, in all of the cases that we talked, always I said that we have access to data, even they are from 5 different countries. We have access to the data from all of 5 countries, but not always it happens. Not always we can get data, and it is where we start talking about federated learning. And we know that, for example, in this case, different countries are definitely different from each other, and it will affect the behavior of the data of the buses. So we know that data are heterogeneous, so we will talk about heterogeneous federated learning. So as a definition, we know that federated learning is a setting that in privacy preserving manner, because they don't want to share their data, the clients collaborate with each other to train a machine learning model. So the only thing that they share, or at least our assumption here, is that the clients only share their models. We know that there are different challenges with federated learning, and for example, communication, cost of communications, or system heterogeneity, privacy, and lots of other things. But the things that here we want to focus on that is a statistical heterogeneity between the samples from different clients. Another thing, what we want to do is analysis of heterogeneity from domain adaptation point of view, and we will see that we simulate different type of heterogeneity, and we want to see how it affects. But before going into details, the setting that we consider, we know that there are different settings in federated learning: horizontal, transfer, or vertical. In horizontal one, the samples of all clients have the same feature sets. In transfer or vertical, it is different. Maybe their features are not the same, or one of them is overlapped by others. There are different, but the thing that we consider, the setting that we consider here is horizontal. That all of the data that we get from all the clients have the same features. And the heterogeneity is in the data, it is a statistical heterogeneity. And about the configuration, that we know there are different configurations. We can consider different configuration, but we use the simplest one, that we have one server and all of the clients are connected to this server. And one more thing is that the clients only share their models. So these are the configurations and setting that we consider. And now we want to analyze the heterogeneity. We define 4 types of heterogeneity between clients. In the next slides, I will go through all of this. And for this analysis, we use a data set that is from predictive maintenance area, that is for fault identification. And we use that to simulate these scenarios. And here at first we use Fed average just to show how this heterogeneity affects the results of the Fed average. And that Fed average is simply the average of all of the local models. Then we will show the results of global model and 1 or 2 client models. So we start with the first one. We say unique global and uniform locals. What does it mean? For unique global, assume that it is our global data. It means that if we gather data from all of these clients, it would be the data that we have. Assume that client 1 has data and exactly the distribution of data is same as the global data. Client 2 also has the same, and client 3 also has the same. So all of them has the same distribution. What is the example of that in the real world? Actually, it is not realistic, but it is like that the companies have the same machine. and that machine operates under only one load. So statistically, there wouldn't be any difference between the data. And this is the result. And actually here we simulate 8 clients that are working on the same loading conditions, and this is the result. We have the results of centralized models, which is in gray. That it means that if we had access to all of the data, it was our result. We had the global model, which is in black. Client, we randomly select clients, one of the clients, and we show the results with federated learning and without federated learning. And in this case, we see that there is not difference between the results with and without federated learning, because the other clients have the same data. There is no heterogeneity, so it can't benefit from those. And also it has enough data.
So it's the amount of data in one client is sufficient.
Yeah, of course. Here, if we have enough data, when there is no difference between this client with other, there is no benefit for that.
Okay.
Maybe that's one that the client doesn't have enough data, this one. Unique, global, and heterogeneously distributed. Assume that we have this global data. Client 1 has data like this. Client 2 and client 2. So all of them together shape that global distribution, but none of them have enough data to see all part of that. So in this way, they are different from each other. But the thing is that they are not in conflict with each other. They all help each other. They just, for example, they just don't have enough data, or data are imbalanced between, in different ways, are imbalanced between different clients. And this is the results of that. Example of that is that different companies using again the same machines under one loading condition, but because of the situations, some faults are more probable to occur in some companies other than others. So data are imbalanced, and some companies have some type of faults, the others have other different types. And this is the results. We can see that, for example, here client 7 can benefit a lot from federated learning. If it doesn't join the federated, the result will be like something like 50 or 60.
And the points where the orange crosses the black one, that's when you do a merge on the central server.
Yes, yes, exactly. The third scenario is mixed global and uniform local. What do I mean by mixed global? I have shown these 2 different signs. That it means if we had all of the data together from all clients in some part of the space, they are in conflict with each other because the distributions are different. For example, client 1 follow this one, client 2 again this one, but client 3 follow this one. So in this way, in this case, even if we had all of the data together, there were some conflicts inside them. And it is, I assume, the most common one in heterogeneous federated learning. And it is exactly, as I said, there are conflicts, and it is exactly the situation that I said. For example, one sample in one company can be normal, can be considered as normal. But if we had exactly the same sample in another country, another company, they would consider that as faulty. It is not that healthy data for another country, and it means the conflict between them. Here it is the results of those. Here we show the results for 2 different clients. And I wanted to show that not always all of the clients benefit from that. And it is because of maybe some of the clients, the data that they have is complex enough to capture the distribution of a whole part of that. So for example, for the blue one, if we want to use global data, it is even less than the performance of that is even lower than the performance of itself. And the last one is mixed global and heterogeneous local. So again, similar to previous one, we have conflict in global data. It is like this, that client 1 follow this distribution and client 2 follow all of this distribution. It means that not always there are conflicts between different clients, but also we have conflict in inside of some of the clients. So in this case, it is the worst situation because we also need to solve the conflict of every data that we get from every client, and this is the result. If I go to this one, it is easier to compare. We can see the last one, even the results of the global model is not as good as the others. And it is because we had conflict inside some of the data of some clients. And that conflict makes that local model weak. And the weakness of that client makes the results of global model worse. Just to clarify, I want to show this again here. For example, here I said client 2, the data of client 2 itself has conflict. And this conflict inside the client destroys the performance. Or maybe we can say it needs more communication or federated communication to converge. So here we see that how the heterogeneity, that it is in 3 cases, affect the results. But in all 3 cases, we see one behavior in all of the local results. And it is like this, that we have drop, and again, it goes up and down. And it is related to catastrophic forgetting. What is catastrophic forgetting? It is a phenomenon in continual learning. That we have a task, we train a model by this task, and we use that model for another task. We start to retrain that model with the data from new tasks. And this model starts to forget information from previous tasks because it wants to get bias to the new task. And here we have exactly this one. In that point, we replace global model with local, and the client start to retrain that model. And when it starts to retrain, because it wants to get bias to the data that it has, it removes its generalizability. And it is one of the main reasons that for heterogeneous federated learning, we need more federated communication, because every time it gets biased, and again it should go up to reach the point. So if we remove the heterogeneity, we will minimize this amount of forgetting. And if we minimize this amount of forgetting, then it would converge faster. If we want to actually connect it to the situations from domain adaptation point of view. The first one, that we don't have any heterogeneity and we have data, it is like traditional machine learning models, that we have one distribution, source and data are from that distribution, and everything is fine. The second one is equivalent to covariate shift. And the thing that we need to do is inner client adaptation. It is similar to that part that I said. We need to minimize difference between probability of X without considering Y. This one that we had conflict in the global, but none of the clients had conflict in their data. It is equivalent to concept shift, and we need inter-client adaptation. We get data from this client and we get data from another client. The only thing that we need is to align. We don't get data, actually, we get model, but we should make sure that it is aligned to each other. And the last one, again, it is equivalent to concept shift, but here we need inter and intra-client adaptation. Even for the local models, we can simply use, for example, MLP for as a model that every client trains. We should force all of the clients to train a model that removes that heterogeneity inside themselves. Then, and if we do that, then we can improve the results. All of things actually are about improving the results. Without doing that, we will get some results. We may need lots of federated communication, but just improving the results and reducing the number of communication, these are some things that we need to do. For the first one and the second one, because there is no conflict between the data, only one global model solves the data, because all of them help each other and none of them are in conflict. But in the second and third one, because we have concept shift and the difference is in probability of Y, sometimes we need more than one global model to find which. So here we need to have methods to capture the similar clients, the clients which are not in conflict with each other. Of course, I'm not giving the solution for how we can find those similar clients, but it is I am just analyzing different situations. So until here, we showed that experimentally, that how the heterogeneity between the clients affect the results and what we need to do. But how does it theoretically true? Here we need to back to the, again, this type of slides. It is exactly what we had, just as a review. We assume X as input space, D as distribution. We consider the binary classification. We have hypothesis H and risk of hypothesis. This is what we had in learning theory. This is what we had for domain adaptation. As a summary, it was the difference between the simple learning theory and the domain adaptation, that we need to minimize the distribution distance between source and target. Now here we want to talk about federated learning. In federated learning, we consider every domain, every client as a domain. So we have a set of clients. For example, we have K clients, and a global hypothesis or global model is simply the ensemble of the predictors, like what we have in Fed average. So we perform analysis for a random client. For example, this one, we consider this one, and we consider this one as target. Any other client is source. And according to the domain adaptation, we have this formula for any two clients. So we can have this formula for any pair of this. In all of the cases, K prime is target and the rest is source. So we can have all of this, and by summing up, I don't show the proof, but if we sum up all of them, we will reach this point. Again, K prime is arbitrary client, K is any other client. And we have this formula, and what does it say? It's that the risk, the amount of the risk of global model over a client, which is K-prime, is upper bounded by this case. These are similar to previous one. The risk of each model on the other clients, but the most important one for us is this term. Oh, yeah, this term. Maybe if I go here, it is easier to see. The risk of global model on any arbitrary client is upper bounded by the distribution distance between that client with the other clients. We have a sigma over all of the clients here, and dh, delta h, means distribution distance between this client and any other client. So if we want to improve the results and make sure that our global model has enough generalizability for every client, we need to remove discrepancy of this client with any other client. This is what we can get from this formula. So here, first, we experimentally show that how this heterogeneity affects the result. If you want to see the more details of that, this is the paper that you can check. And here we show theoretically that how the diversity between clients affect the result of global. And this is, if you want to see the proof of that and the details of this one, you can find in this paper. We have submitted this one, but yeah, we are waiting for the answer. But a bit more detail about this one, by having this intention that, okay, we need to remove heterogeneity between this one with every client with the rest, we propose a method. I don't want to go to details of the method. Actually, this is my last slide. I just wanted to introduce this one. And I say that, okay, by having that formula and knowing that, okay, we need to remove heterogeneity, we propose this method that server train a generator for every client. And that generator is trained so that capture the conflict between this client with the rest of the client. So, and here every client, by in addition to its own data, generate some data from generator, and then using all of the data, train the local model and send a local model to server. And similar to Fed average, we ensemble all of the local models. Okay, actually, it is my last.
You don't have more slides on this, but how does it perform?
If we
does it solve all the problems that you mentioned earlier?
If we compare with Fed average, yes, we saw lots of improvement in the accuracy, yeah, and also it reduced number of the needed federated communication. For example, if Fed average after 100 communication reached, for example, 60, that method reached 60 after, for example, 10.
Exciting.
But if we compare with Fed average. Anyway, the more details of this method is in this paper. You would like to check. And yeah, thank you.
Thank you. So now it's your turn to bring up all your questions for Zahra. And while you think about the most intriguing questions here, perhaps I could ask, the experiments, you talked about machines, but did you describe exactly what kind of data that you were using for federated learning experiments?
For those simulations, you mean?
Yes. Is it simulated data?
No, the data were from the real world data.
Yeah.
But it was vibration data.
Okay.
Yeah, and then we applied a fast Fourier transformer on that, and then we had, yeah, I can't remember exactly the length. I think it was 500 something. Yeah. But the data itself was vibration.
And the task was some predictive maintenance then?
Yeah, the task was fault identification, that we had 5 different type of faults. And then we use. And for the model that we use, that all of the client trains, it was just MLP. And yeah, and the federated method was fed average.
Questions? It always leave a long time for people to come up with questions. That's my experience.
May I ask a question?
You're not getting away without asking any questions.
Olof, may I ask a question?
It seems someone has questions.
Or is there something in the chat? Okay, so we have an old question in the chat. Conditional distribution shift. The conditional here is the Cannock tree. With a question mark. But that was earlier in the presentation here. We talked about the conditional distribution shifts.
Yep, for that one, for that paper, we consider different type. One of those was country. And we actually, by some analysis on the data before going into domain adaptation and applying domain adaptation on that, by checking the distribution of data, we figure out that, okay, there are really distribution shift between the data from the different countries.
Cool.
Where the name of dark comes from, okay, it is, let me show you.
I mean, it's not just a cool name.
No, it was a domain adaptation under conditional distribution shift. D from domain, A from adaptation, C from conditional and distribution. We just changed it. That was my question.
Great. We have one final question. Is the model capable of detecting heterogeneity after removing outliers and faulty data? Perhaps you need to clarify your question.
Actually, yes, here we didn't consider that data includes outliers.
Yeah. You did not remove any outliers.
There were, yeah, we did.
Okay.
At first, but there were obvious that they are outlier.
Okay.
We didn't apply outlier detection method on that, but just by doing some data analysis, some simple task, some data were obvious that, okay, they are not real data.
Another question, have you experimented with other methods like invariant risk minimization, given that it was a linear problem rather than domain adaptation?
No, actually, invariant risk minimization, no, we just compare this domain adaptation methods.
Yeah. Perhaps that's something to look into for the future.
Yeah, exactly. Yes.
Do you have other plans of what to do in the future work?
Yeah, actually the work that now I'm working on that, maybe I can talk a bit about that. It is about federated learning and exactly federated learning for regression when we have heterogeneity. Because I would say almost all of the methods that are proposed for heterogeneous federated learning are for classification. But solving regression is a bit challenging. This is one thing. And another thing is having more than one global model. There are some studies on that, but the thing is that how we define that similarity between clients, that we don't lose information, not always finding the most similar clients and merging them is beneficial. Sometimes we need some different clients to merge with them in order to help them. If I beg. Okay, the second part, actually, I want to show you. The second case is this one. Here, when we are in this situation, that usually the methods that wants to have more than one global model, they compare or they define similarity based on the amount of loss that they have in the retraining global model or something like that. But in this case, maybe we merge, for example, the first and second one together and the third one keep it separately. Mm-hmm. Because they are different from each other. So their data, their models are totally different from each other. And the conflict is in their model, not in data itself. Mm-hmm. So if we separate them from each other, they will lose information. Because in this case, there is no conflict between data. And it is a bit tricky how we define that similarity to merge clients that benefit each other. Mm-hmm. Also, there exists some conflict between models, not data. And the tricky part is that conflict in the models that are trained and are not well trained because they don't have enough data from global. They don't have overview of the global, or it is just the real conflict between them. Mm. It is the thing that we are working on that. We have done something, but it is not finalized. So these are two different directions: federated learning for regression and also finding more than one.
Great. So looking forward to hearing about that in the future then. Mm-hmm. And thank you very much, Zahra, for this talk.
Thanks.
Everybody, welcome back in 1 week. We will have Adam Breitholt, who's a PhD candidate at Chalmers University of Technology. And he will present here at our office in Gothenburg. And we will, as usual, also be on Zoom. The topic is going to be also about domain adaptation, but in that case, not federated learning, but privileged information, unsupervised domain adaptation by learning using privileged information. So welcome back next week, 7th of September.